like on their website.
Okay, let's get started, please. So, I have the impression that people were a little confused at the end of class. So let me just sort of sketch out in a little bit more detail the last part of the proof of the nowhere differentiability of Weierstrass's function. Okay, so remember what we did. We chose these delta m's that were plus or minus a half times 4 to the minus m. Okay, so so here's your x, and we have these points x plus delta m. Okay, and the whole idea of the proof is that we're going to look at the function f of x plus delta m minus f of x over delta m. Okay, we're going to look at these things. Okay, and we're going to show, we'll show that this thing is bigger than 1/2 3 to the m plus 1. Okay, so what's the point of that? What is this thing here? This thing is the slope of the secant line through these 2 points, right? And so what this is saying is that if you take from here to here, the slope of the secant line, right? The slope of the secant line exceeds this certain number, okay? Further, as m gets larger, right? So this is delta, now let's say that this is delta 1, okay? Well, where's delta 2? Delta 2 is going to be a quarter of the distance closer, right? It's going to be a quarter of the distance closer. So, you know, it's going to be this distance. It's either, but because of the plus minus, it's either going to be on the right or on the left, right? So let's say it's on the left. This is x plus delta 2. And then what is delta 3 going to be? Well, it's going to be a quarter of the distance closer, right? So x plus delta 3, and so on and so forth, right? So these guys, x plus delta 1, x plus delta 2, x plus delta 3, right? They're getting closer and closer, whoops. They're getting closer and closer to x, right? But what's happening to the slopes of the secant lines? The slopes of the secant lines are increasing like 3 to the m, right? With every step, you basically get multiplied by 3. Okay? So what does that tell you? You can't be differentiable, right? Because to be differentiable, you need the limit as h goes to 0 of this thing to be finite, right? But here we're seeing that there are all these bad points where the limit is going to tend towards infinity on some sequence that converges to x. Okay. Okay. So that's the idea, right? And the argument went like. The argument that we did was we said, well, we broke this down into its pieces, and we saw that it equaled 3 to the m plus summation 3/4 the n gamma n, as n went from 0 to m minus 1. We also knew that we also showed that the size of gamma n was less than 4 to the n. Yeah.
Professor, you were saying secant line. What do you mean by that?
Secant line. So when you have some function and you're trying to get the slope, the derivative, the way you get it is by taking the limit of the slopes of what are called secant lines. So secant line just being a line that passes through these 2 points on the curve. Okay. So right, this line here is called the secant line passing through these 2 points. Okay. And normally, right, when you're trying to get a derivative, right, the derivative is going to be the limit of the slopes of secant lines, right? The slope of this line, right? You take the secant line through x and x plus h, and you let the second point tend towards x by letting h go to 0, right? So you take the limit of the slopes of the secant lines, right? Well, right, what we see here is that limit cannot exist, right? Because no matter how small your h is, there's some delta m there's an infinite number of delta m's in between that h and your x, where the slopes of the secant lines head off towards infinity. Okay, so this is where we got, right? And this is where I think people got confused, but it's actually not that confusing. You say, well, look, by the reverse triangle inequality, by the second part of the triangle inequality, you know that this is bigger than this. Right? You know that this is bigger than this. Okay, and then what you notice is that this term, I can pull the absolute values off of this term. Okay, so notice that I can get rid of the absolute values, right? So observe that that this thing minus this thing is positive. Is positive, right? Why? Why? Well, what is the biggest thing that this could be? What's the biggest that this could be? This term here, right? At most, right? The term is greatest if lambda n just equals 4 to the n. Throughout, right? We just take lambda n, I'm sorry, gamma n, let's just let it be 4 to the n, right? Right? So in that case, we get, summation 3 towards n, 4 to the n, right? As n goes from 0 to n minus 1. Right? So you get 3 to the m minus this thing, right? But that's still going to be positive, right? That's still positive because, so well, what's this thing? Summation m minus 1, n equals 0, 3 to the n equals what? Does anybody remember the formula? Or just redo it in your head right now? 1 minus 3
power m divided by 2.
Divided by
2.
Negative 2.
Negative 2.
Yeah, by negative 2. Right? Right? The partial sum of the geometric series. Right? Because you take, right, if you have some geometric series, 1 plus r to the n minus 1, and you multiply that thing by r, you get r plus r to the m, right? You subtract, you get 1 minus r equals 1 minus r to the m, right? So times s. So s is 1 minus r to the m over 1 minus r, right? Okay, so you get 1 minus r to the m over 1 minus r. Okay, but so this thing is going to be 3 to the m plus 1/2 of 1 minus 3 to the m. Right, because I subtract and I've got the minus 2 on the bottom. Right? Right? But what is that? Right? That's going to be 1/2 of 1 plus 3 to the n, which is bigger than 0. Okay. So no matter what this term is, the difference is going to be bigger than 0. Right? So I know that this, I'm going to subtract off, this is going to be bigger than 3 to m plus 1/2, 1 minus 3 to the m, which is this 1/2, 1 plus 3 to the m, as designed. Right? And so we get our bounds. Yeah?
The bounds is on absolute value. How do we conclude from the fact that absolute value diverges, the original thing diverges the slope? Because we're trying to prove.
Yeah. But if the absolute value gets infinitely large, certainly this thing has the magnitude of this thing is infinitely large. It's either a huge upward slope or a huge downward slope, depending on what side of our function we're on. Right? Our function looks something like this, right? It's some sort of fractal thing is what it is actually. So depending on what side, we'll either have a huge positive number or a huge negative number. Okay. 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 So you see that this was a pretty cool application of a lot of ideas. Uniform convergence, right? We needed the uniform convergence. The reason that we know this is continuous is because we have that theorem about uniform convergence of continuous functions, right? We're taking a sum of continuous functions. This guy is going to be continuous, right? And we needed Weierstrass's m-test to show that we actually did have uniform convergence. Right? Without these ideas and these tools, this function, it would be impossible to show that this function existed. Yeah, Faye?
Give me an intuition for what it looks like.
For what it looks like. Well, remember what happens, right? We've got this thing, and then we speed it up 4 times, right? We sped it up 4 times, like this. Right? Maybe like this. Yeah, that's what it is, actually. So we have the original absolute value function, right? And then we sped it up 4 times, right? So this, right? So what you see is that you're taking this original guy and you're adding on spikes to it. Okay, you're adding on spikes to it, right? So, but then you're taking each of those spikes and you're adding on faster spikes to those guys. And you keep on doing that in an iterative manner. Okay, and so at every point, there's just spikes of increasing height being added on. Okay, have you ever heard of the Koch Snowflake? Yeah, it's something similar to that. It's something similar to that, right? You take your line, and then you add a spike onto the line, right? And then you add on smaller spikes to each of those lines, right?
Yeah.
Right? And then you take each of those lines and you add on smaller spikes of size, geometrically decreasing size, right? Spikes of geometrically decreasing size to them. This is exactly the same sort of construction. Okay. Yeah. If you look on, just Google Weierstrass's nowhere-differentiable function, and people have used MATLAB to graph it out. Yeah.
There's actually an animation.
There's an animation of it.
Yeah.
Okay, great. So, Abel, you can hold it up to Fei-Young.
Here.
That's as you add on the spikes. Awesome. Okay. Okay. So the moral of everything that we've done so far in this chapter is uniform convergence is good. Okay. Right. That's basically the only very crude moral we've got here. Okay. Uniform convergence is very good. Okay, so what we're hoping for in the rest of the chapter, well, in the next result that we're going to go for is basically telling us when can we get a uniformly convergent subsequence. So you've got a sequence of functions, and you're wondering when does there exist a uniformly convergent subsequence? Okay. So this is kind of analogous to what we did before. It is perfectly, in fact, analogous to what we did before. The problem of if you have a sequence of points, when do you have a convergent subsequence of points? Right? Does anybody remember the result that we had at that time? I don't even know if we gave the proper name. Does anybody? Yes.
So if the initial sequence is bounded, then there's a convergence subsequence?
Yeah. Yeah, so the Bolzano-Weierstrass theorem, so recall back in Rn, right? In Rn, if you have a sequence is bounded, you have an infinite bounded sequence, then you're guaranteed that there exists a convergent subsequence. Okay. And this is called the Bolzano-Weierstrass theorem. Okay. Now, we want to do something similar for functions, right? We'd like to say, if you have some sort of condition on a set of functions, then you're automatically guaranteed a convergent subsequence, a uniformly convergent subsequence of functions. Okay. So we have to define what we mean by bounded, right? What does it mean for a sequence of functions to be bounded? And there are two sort of candidates for that notion. So different types of boundedness of sequences of functions. Different types of boundedness for a sequence of functions. Okay, so the first one is kind of a simple one, and it's going to be the unsatisfactory one. So you start off with a sequence of functions. On a set E. And yeah, so these functions for us will be complex valued functions, but yeah, okay. So if for all x in E, fn x from n equals 1 to infinity is a bounded sequence, then we say Fn is pointwise bounded on E.
Professor, why did you say that it only exists in complex functions?
Well, just because that's what we're gonna do it. I think I mean, you can do this in a more general setting, I think, but we're gonna do this for complex functions, complex valued functions. Okay. So so for example, so what is this saying? This is saying that you have some set, right? Let's pretend that our set is some interval, right? And what this is saying is that if you look at any point in the set, then the fnx, right? You have some f1x, you have some f2x, right? f3x, right? f4x, whatever, right? And those guys have to be a bounded sequence. Okay, so for each point, there's a bound, right? For each point, there's a bound, right? So the bound, right? For each point, there's a bound on the sequence. Okay, and in that case, we say it's pointwise bounded, right? Okay. Now, the second type of boundedness is stronger. So, wait. So, equivalently, there exists a phi such that fnx is less than phi of x for n equals 1, 2, 3, etc. Okay? This phi of x is just your bound at x, right? The bound at point x. Right? We said that at each point your sequence is bounded. By what? This is the what. Okay. It doesn't mean, however, right? But your phi of x could head off towards infinity. That's fine. Right? Your phi of x could be something like this, right? So this is your phi of x. Well, at each point, right? Let's say that at e is like this, right? Right? At each point, your sequence is bounded, right? But it's not to say that that bound doesn't head off towards infinity. Okay. Now, the second type of boundedness is called uniform boundedness. So if there exists an M such that fnx is less than M for all x in E and for all n, then we say Fn is uniformly bounded on E. Okay, uniformly bounded on E. Okay, so this is different, right? What this is saying is that you have your set E, but there's this M that and everybody is trapped within it, right? Right. That M works for all points. That M works for all points in E. Right. Your functions are trapped, right? Right. Right. So basically, all we're saying is that in that case, the phi function is a constant, right? The bound function is constant. Okay, so we've got these two notions: pointwise boundedness of a sequence and uniform boundedness of a sequence. Okay, and neither of them is what we want, actually. Neither of them is exactly what we want, but well, let's see what happens. Okay. So so our first question will be, under what conditions on our sequence do we have a pointwise convergent subsequence? Under what conditions can we get a pointwise convergent subsequence? Right. So we have, remember, we've got two notions of convergence. Right. One is the unsatisfactory pointwise convergence. The other is the very good uniform convergence. We're going to ask the first question. Is there some sort of boundedness that gives us a pointwise convergent subsequence? And then we're going to ask, is there some sort of boundedness that gives us a uniformly convergent subsequence? Okay. Right. And so one initial guess, you might think something like, suppose that the Fn are uniformly bounded and they're continuous functions on a compact set. Right? You throw all these conditions on, and you think, maybe, is that enough for me to get pointwise convergence? Is that enough to guarantee a pointwise convergent subsequence. Right? And it turns out the answer is no. The answer is no. And the counterexample that Rudin gives looks like this. So it says, well, look, let fnx be the sign of nx function on the interval 0 to 5. Okay. That's certainly uniformly bounded, right? They're all bounded above and below by 1, right? By 1 and -1. They're all continuous. It's a compact set, right? So we're hoping that that's enough to guarantee a pointwise convergent subsequence, right? Thinking, okay, maybe I can get a pointwise convergent subsequence from these guys. Okay, but suppose there existed a pointwise convergent subsequence. Subsequence fnk. Okay, so you were able to choose some frequencies, and you're hoping that those frequencies are going to get you convergence, right? That would mean that the limit as k goes to infinity of sine of nkx minus sine of nk plus 1 x is 0. Equals 0 for each x, right? Right. Yeah, it doesn't occur at the same rate, but at each point, this limit would be 0. Right? That's what pointwise convergence means, right? That at each point, this limit is going to be 0. Right? But in that case, that would imply that the limit of the squares is also 0 as k goes to infinity. Okay. And that would imply, via a theorem that you don't know yet, that the limit of the integral over that interval of the squares would actually be equal to 0. But it turns out to be 2 pi. If you work it out, it just turns out to be constantly equal to 2 pi. Okay, so this is a theorem that you learn when you take 137, the Lebesgue dominated convergence theorem. That it's okay to in this case it's okay to pass the integral through the limit, even though we don't have uniform convergence. Okay, remember we have a theorem about interchanging limit and integral, right? If the series converges uniformly, but this is pointwise convergence. However, it satisfies the conditions of this thing called the dominated convergence theorem, which says that you can't do it as long as certain things happen, certain things are satisfied. Okay.
Professor?
Yeah.
In the step on by taking limits, I was wondering if there are any points between sine nkx and sine nk plus 1x, because like taking the difference implies that there are points in between. Like why are we not just doing sine nkx minus sine nx?
So we're just giving what we know is that the sequence converges pointwise, right? So that means that the limit of this thing that tells you that that this sequence is for each fixed x, the sequence fnkx That's to say, sine n kx is convergent. Well, that means it's Cauchy, right? Right. So that's going to tell you that. I mean, you don't even need that actually, but that will imply that this difference goes to 0. Right? Actually, you don't need that. You just need that the limit exists. But anyway, Cauchy is enough. Yeah, Susan.
What's in the here again? So is it like some sine cosine formula?
What's in here?
Yeah.
The same thing here. I just squared it.
Oh, okay.
The same thing as above. So sine minus sine. Same thing. Okay. Okay. So so what we see is that even if you have continuous functions on a compact set and they're all uniformly bounded, you're not guaranteed a pointwise convergent subsequence. Okay. And we're going to get a result that seems kind of weak, but it'll turn out to be useful in what we do later. Okay, so weak but useful result. Maybe I shouldn't call it weak. It's useful. So, okay. So the following is a kind of partial result that will be useful to us when we go for the big theorem of Ascoli-Arzela. Okay. So, and the result is on countable sets. Okay. So here goes. Suppose you have a sequence of complex value functions on E. If you know that E is countable, and you know that the Fn are pointwise bounded, then you're guaranteed a pointwise convergent subsequence. Okay. So, right, given any pointwise bounded sequence of functions on a countable set, you're guaranteed a well, C-valued functions on a countable set, you're guaranteed a pointwise convergent subsequence. And this is basically using Bolzano-Weierstrass and Cantor's diagonal process. So here's the idea. You say, okay, let's denote E as a sequence of points xi from I = 1 to infinity. So let's give names to this countable set, right, to the points in the countable set. And we say, okay. And we say, okay, let's look at the values of Fn on the first point, right? N from 1 to infinity. Okay. So this is sort of like pretending that our set consists of only one point. Okay? If our set consisted of one point, well then, what do we know? If we look at the values, all these values, right, are bounded, right? All these values, we've got a bounded sequence, and so what do we know? We've got a convergent subsequence by Bolzano-Weierstrass, right? Right. This is a bounded sequence of points, right? It's a bounded sequence, right? Because we know that the Fnx are all less than some phi of x, right, for all n, right? Right? It's a bounded sequence, and so by Bolzano-Weierstrass, says there exists a convergent subsequence. F and K x1 from K equals 1 to infinity. Okay. Okay. Now we're going to step to the next. We were going to step to the next point, and the way we do that, well, let's introduce some notation to make it simpler. Okay. So notate. F1k is going to be Fnk. Okay, so by this notation, this 1 means that so this means that we're the kth member of the subsequence that converges on x1. Okay. Right. Right. This Fnk was the subsequence that converged on f1. Right. So I'm going to call that subsequence f1. Right. F1. The guys who converge on x1. The guys who converge on x1. The kth member I'm going to call f1k. Okay. So you've got this sequence, right? It's going to be f1, f1, 1, f1, 2, etc., etc. Right? Right. Instead of writing fn1, fn2, I'm going to write f11, f12, f13, etc., etc., to denote that these are the guys that converge on the first element. Right? Converge for x1. Right. If I evaluate them in x1, these guys converge. Okay. Okay. And so what you do is you say, well, okay, now I'm going to look at, consider f1 and x2 as n goes from 1 to infinity. Right. So I've got my sequence here. I use that subsequence as my new initial sequence. And I say, okay, I know if I look at x2, then I know that there's going to be some subsequence that converges on x2, right? Because all these things are bounded for the exact same reason, right? This is bounded, and so Bolzano-Weierstrass tells me that there's a convergent subsequence of those guys, right? Right. So there exists a convergent subsequence f1 n sub k x2 as k goes from 1 to infinity. Yeah.
F sub 1 or F sub 2?
F sub 1 for now. For now. Okay. Right. Just to say that we take our original subsequence and we take a subsequence of that subsequence. Right? But you're right. In a second, I'm going to call it F2. Okay. So, as Edward has noticed, we're going to notate that guy F2k as F1 n sub k. Right? So this is the sequence that like the kth term of the subsequence, right, that converges on x2. Okay. So it's easy enough, if you had a finite number of points, you could just stop after a finite number of points. right? You just keep on going. If I've got, a billion points, you would just stop at f sub a billion, and that guy would converge on all your points, right? Because you'd have a subsequence of the subsequence of the subsequence, blah, 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 and the last guy is going to converge on every point, right? But I've got infinitely many points, and so I can't stop at some point. I have to use the Cantor's diagonal process. Okay, so in this manner, we obtain, right, we get this f11, f12, f13, f14, etc. We get f21, f22, f23, f24, etc. f31, f33, f32, f33, f34, etc. We get this huge array of functions. Okay, and right, where each row is a subsequence of the prior row, of the row above, right? 2, the nth row converges on xn, and actually all x1 through xn. Right? And the kth element of the nth row occurs in the n sub kth place in the n minus 1th row. Okay. Do everybody understand what I mean? I mean, the first two are pretty straightforward, right? This row is a subsequence of the previous row. This guy converges on x sub n, right? This one is saying that if you look at the second term here, right, then that term occurs past the second term here, right? The kth term occurs past the kth term here, right? Because this is a subsequence of the former guy, right? This 2, right? 2k is actually 1 n sub k, right? But n sub k is greater than k, right? N sub k is bigger than k, right? Because it's a subsequence, right? N1. At the very worst, n1 would be 1, n2 would be 2, and 3 would be 3. But if there's any skipping at all, then n sub k is going to be strictly greater than k, right? So the kth term of this nth row occurs in past the kth term of the previous row. Okay, right? So this guy occurs after. At worst, it occurs here. Maybe it occurs after here. Okay. Okay. So you can. So the result is that thus if we go down f and n x sub k n equals 1 to infinity, this thing converges for every point x sub k. Okay. So try to write it down rigorously. So this is the idea. This is the idea. You need to write down this last fact a little bit more precisely. But this is. I hope you see the idea, right? Like, think if I were looking at x1, and I'm looking at this. I'm saying, oh, what happens to x1 here? Well, x1, f11 of x1, I got f11 x1, f22 of x1, but that occurs farther down, right? I know that this thing's sequence converges on x1, right? And I know that these guys are occurring later than their kth term here. So I can definitely get, if these guys converge to something, then the sequence is going to converge even faster, right? Because it advances faster down the line than the original sequence, than the original row. Okay, and same thing for x2. Same thing for each point. You're going to get a sequence that advances faster than the original row, which converges to some value, which converges. Okay, that's the idea. Yeah, Lara.
So you said that the subsequence will be equal to or greater than the sequence itself.
The index is going to be greater than or equal to the index here, right? So this guy is f1 and k, right? But that's right. You started off with the original sequence 1, 2, 3, 4, 5, blah blah blah, and then you've chosen n1, n2, n3. All we're saying is that n2 is bigger than 2, n3 is bigger than 3, right? Because at the very worst, you would have something like this. Right? If you chose your subsequence, if your subsequence was the whole original sequence, well then you'd have nk equals, right? nk equals k, nk equals k, right? But if there's any skipping at all, right? If you don't choose the full subsequence, well then your sequence is going to be advancing faster. Okay. That's actually a good place to stop. So we've got a result that gives us a pointwise convergent subsequence. Next time we're going to talk about a condition. Yeah. So next time maybe we'll get to the great theorem, kind of the climax of the course, sort of. The theorem of Ascoli-Arzilla, which says under what conditions we get a uniformly convergent subsequence.